Typically when 5-axis machining, we want to minimize the amount of rotary axis movement as much as possible, as this will generally give much more stable cutting conditions, which in turn will improve our surface finish, and generally our overall feed rate will increase as we're minimizing any deceleration and acceleration of those rotary axes. So to help us achieve this, a new option has been developed on the tool axis definition form that allows us to lock one of the rotary axes of the machine. So we're going to load in an example and go through the procedure of locking one of these rotary axes using this new option. So I have 3 tool paths already created. 1 has already been calculated and 2 are batched, ready to calculate. The first toolpath is a simple constant Z toolpath. You'll notice that we've also used automatic verification to remove any collisions with the shank or the holder using the displayed parameters. So if we zoom in, you can see quite clearly here that the constant Z toolpath is incomplete. There are large sections that obviously collide with the shank and the holder, and these have been removed by the automatic verification. So let's just bring our machine tool back and simulate from the start and display the machine axis information. Just pause the simulation and increase the simulation speed. So you can see, as mentioned, it's simply a 3-axis tool path with a vertical tool axis, so there are no B and C axis movements. An ideal way of machining this part would be to tilt the head over at 45 degrees to allow the tool better access to the part without colliding. So now we're going to use the new fixed tool axis option to force the head of the machine over at 45 degrees and lock one of the axes of the machine. So if we go to the settings for our second toolpath, on the tool axis form there's a new option under the definition tab. You see our tool axis is still set to vertical, so 3-axis machining, but then we're telling it to lock, in this case, the elevation angle to 45 degrees. So in this case the elevation angle is the B axis, which is on the head. If we accept and calculate this toolpath, so you can already start to see that we're machining much more of the part than we did with the previous toolpath. And this time, if we simulate from the start and bring back our machine axis information, let's just pause the simulation and rotate and get a better view. So here we can see that this time the B axis is locked exactly 45 degrees and will not move away from that angle, and the whole part is machined with that B axis locked. If we just escape from that simulation and rewind back to the beginning, if we zoom in a little bit closer, we can still see that there are lots of retrap moves in this region here, lots of skim moves. If we undraw those moves for a second and undraw the part, we can still see some gaps or missing areas in the toolpath, which again is due to the automatic verification removing any colliding regions. So even though we've used a 45-degree tool axis, there are obviously some areas where even at 45 degrees the tool holder collides. So ideally we want to lock one of the axes of the machine, but we also want the flexibility to allow us to move away from that locked angle if there are any collisions, so we can avoid the collisions without having to retract off the part. So to do this, we can use the collision avoidance in conjunction with the fixed angle definition. So on the last toolpath, on the tool axis form, We've also switched on collision avoidance with a lean and lead method, and now if we calculate, here we can see now we have a complete toolpath without any brakes at all. And if we attach our tool to somewhere in this region, bring back our head of our machine, and now if we simulate, you can see the B-axis is locked at 45 degrees, but Powermill has the intelligence to move away from that locked angle to avoid any collisions, still keeping the tool on the job, and then once the collision has been avoided, the tool axis then goes back to the locked 45 degree angle. So here we can see now the axis is deviating slightly, and now it is going to return back to the 45 degrees.